Does anybody have any homework questions? Okay. Three 3.3?
Yeah, my escape.
You know what? I think I'm in the wrong view. Okay, let's look at this real number. This number is constructed by just taking the natural numbers in sequence 1, 2, 3, 4, 5, 6, 7, and so on. The 14th digit 1, 2, 3, 4, 5, 6. Well, this is 10, 11, 12, 13, 14. The 14th digit is a 1. Well, I wonder if they're including the 0. The 14th decimal place, though, is a 1. The 25th, you'd have to keep writing down. 1, 2, 3, let's see, this is 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 17. So 7. And we'd have to keep going to figure out the ones after that. I'd have to just write them down and count them out. So just keep writing it out and counting the digits. Don't count the 0 over here.
I actually had a question on there too. Did you type it in there? No, not that one. No, it was one where we had to actually enter the. I wonder if there was I guess there was an earlier. We actually had to put in the answer, and I didn't know what to do.
Was it where you do the 6 times the n or 3 times the n for the 1-to-1 mapping?
Yeah, that's the one. I didn't know how to actually enter the answer. Like I could write it down, but I don't know how to enter it in there.
So that's how you answer your answer for the 3.2 Mindscape 9. You're supposed to use the times button on the 8 on the number 8. Yes.
So are you just adding 6 every time?
Yeah, it's the 1-to-1 correspondence between the natural numbers and 6 times n, and you don't have a way to say 1 goes with 6, 2 goes with 12, 3 goes with 18. So on Wiley you have to enter it this way. Any other questions? Okay. I wanted to look at the Canvas grades with you. As a student, you can click on the grade tab in Canvas, and then you can put in different prospective grades. So this is me as the test student. I don't do the work, so I don't have good grades. But I can put in prospective grades here and see how it affects my grade. Okay, so that's kind of nice to be able to do. Your quizzes are most of your grade in this class, and if it's not going well for you, I encourage you to go to the home page and print off these reviews and work with them. They're tentative now. They'll be solid a couple days before the quiz when I know what we actually cover. So for example, we just looked at starting section 4.1, and you could have this in mind. This is what I'm going to get quizzed on. This is what I need to be able to do. You could make sure you understand one of the proofs that we're doing for the Pythagorean theorem. Make sure you know how to use the Pythagorean theorem. Okay, so if your quizzes aren't going well for you, this is something you should have in hand. And of course, you can go to the tutor and they'll help you with this in the study groups, or you can have one-on-one meetings with the tutors as well. Does anybody have any questions? When we were in set theory, I had gotten asked what are some real-life examples of set theory. So we did set theory when we looked at different sizes of infinity. So I have this author from the Stack Exchange telling some of the benefits that set theory brings to the sciences. One of the main values of set theory is that it provides a language. So set theory gives us a language. Even computer scientists describe their basic concept, Turing machines, in the language of set theory. And then the idea of infinity gets used in topology. So to thoroughly understand the mathematics behind, say, modern physics, does in fact require, among many other things, that you understand the properties of infinite sets, because topology has become an important part of this mathematics, and understanding general topology depends heavily on understanding the properties of infinite sets. We're going to be looking a little bit at topology in one of our future chapters. As a specific example, the mathematics behind general relativity is called differential geometry. I think it's fair to say the development of general relativity would have been impossible without the mathematical language to express it. Differential geometry takes place on special kinds of manifolds, which are special kinds of topology. So you take the set theory, it gives you topology, the topology gives you the physics that you need for general relativity. In fact, there's one particular article that I have here from Gregory Jabor, who thought it was interesting that his work in the optics of light uses one of the problems that you had in your Mindscapes. You remember that Mindscape question where you had the infinite hotel and the infinite hotel was full and one more guest wanted to check in and you had to find a room for them? Yeah, that is what is called Hilbert's Hotel, and this author is referring to that as part of his work. Infinite mathematics can be realized in optical systems possessing swirling vortices of light. In particular, both demonstrations showed how particular systems mimic exactly a paradoxical thought experiment known as Hilbert's Hotel, in which the occupancy of a hotel consisting of an infinite number of rooms shows very strange behavior. These examples seem to be the first ever showing that infinite mathematics not only manifests in some real-world systems, but is essential in explaining them. And so this is an article that you could understand most of, I think, quite well, and you might enjoy because it does talk about how our studies of the infinite impacted this author's work, his research. Well, we have been working on the Pythagorean theorem in 4.1, so 4.1 continued here. This should be in your notes, this beginning of proof 3. And I'd left you with the weekend activity of finding your fat L shape out of your templates. So let's take your templates, and I saw some of you had the fat L shape before we left for the day. So I'll go ahead and just put that up here, but hopefully you thought about it over the weekend and were able to figure it out. So here you had an L, and then when you put this piece in, you have a fat L, as your author calls it. Okay, so you're going to need a picture of this, so take out your templates and get it laid out. Does anybody need a scissors yet? Now, besides taking a picture of this, you need to know what it stands for. So, did anybody figure that out? I know you spent the whole weekend thinking about this. What did you figure out? What does this stand for? Now the picture we drew was c by c, so it was c squared. And we drew it with these 5 shapes, the 4 right triangles and the square that's a minus b by a minus b. What would we like this shape to stand for? Anybody know what the proof needs this to stand for? So we use these same 5 shapes to make c squared. For the Pythagorean theorem to be true, what does this rearrangement of these 5 shapes need to be equivalent in size to?
A and B squared.
Yeah, a squared and b squared. So let's see, do you see any squares in there that are a by a?
Oh, like the top part counting the square, kind of, right?
Yeah, good. The top part counting the square. So if I put this marker and divide it off, above the marker we have a squared. Now you can see it's a across because you've labeled your template a. But this height is a little harder to see. This height is b, and then you have the square besides. The square is a minus b in height. So if you combine b with the square a minus b, you get the height a. Because remember, this square is created by taking the side that's length a and removing b and using that length. So we take the side that's length a and remove b to get this length. Well, then I add the b back in. So now we're back to the length a again. So this is a tall and a across. And then the little square is b by b, because you have b across at the bottom, and then you have the vertical length of the red triangle is a, but I've taken away part of that. I've taken away the part that's a minus b long. When I do that, I get this length b, because this whole length a, I created the square by measuring b against, and when I took the b away, then I had the a minus b. So this part right here is the b. So it's b across and b up. So this is the a squared plus b squared made out of the same shapes that we made c squared. And this is another proof of the Pythagorean theorem. So we're going to copy this down, but before I move it, you might need to take a picture of your own templates, right? So put your own templates out, put your name placard there, okay, and take your picture. And why don't you upload it right away? I mean, we have a minute here while we're drawing, and then you can get it uploaded and not get it mixed up with some of your other photos that you get taking later on in the week. So this is 4.1. 4.1 class activity. And you have to tell what this is, and when you tell what it is a squared plus b squared. You can write out the square, and you don't have to put superscripts. You can write a squared plus b squared. Yes. Then we'll copy this down onto paper so that you have proof 3 ready in case that's the proof you like best, and that's the one you want to use on quiz 2. Okay, so let's get drawing this on our paper. How would you use this in your proof? I'm going to draw a rectangle, and I'll make it 4 units by 7, and then I'll draw the other rectangle, and then I'll cut them on the diagonal, and then I'll add the square. Now you don't have to be 4 units by 7. You can be whatever measurement you want, just so you're consistent. So we're looking at proof 3. It's the least amount of algebra, but everything has to be well labeled. So we have our two rectangles that we formed into right triangles. So those should be sketched the same size. I sketched mine 4 units wide and 7 tall. You can draw it how you want, okay? But then when you go to make the little square, you find your width like we did for the width of the square.
Do you have to take a photo of that too?
No, the photo should be of your templates that you cut out.
Oh.
The photo should be of the templates that you cut out. So when you make your square should be this height here. So in mine it's 3 by 3 because 7 minus 4 is 3. So I can make this bigger now and move this off. So we label the A, B, and C. So A was the longer leg. B was the shorter leg, just to be consistent and to match your other drawing. And C is your diagonal, your hypotenuse. And these are all right triangles, these 4, so they should have a corner to show they're a right triangle. And you should have notated your length here as A minus B in the square. So these are the same area, and we show that by labeling with the same letters. So the A over on this picture is supposed to be the same length as the A over on this picture. Now we're not doing this with a computer, we're doing it by hand. So to make up for not having exactly the same, we label the same. So this A is supposed to be this A, this length B is supposed to be this length B, and so on. Well, that's your general picture, but then you have to show that there's an A squared on the top. So draw a little dotted line and show this is your A squared on the top, and then B squared on the bottom. And then you can say C squared equals A squared plus B squared. So the least amount of algebra, but you have to label everything carefully and make sure you indicate where A squared is and where B squared is. Anybody have any questions? Okay.
Sorry, just like the photos 4.1.
The class activity for 4.1 was the photo we just took, yeah. So all these 3 proofs could be done with any proportioned right triangles. They don't have to be ones cut with the same proportion. So here I have the similar fat L shape made up with a different proportion right triangles. I lost one. That's weird. Okay, well, you get the idea. You're going to have the same proof with different proportion right triangles. That's why we just use A, B, and C and not 3 by 5 by 5.83 or whatever that hypotenuse was. Any questions in 4.1? Everybody feel good about one of the proofs, hopefully? Okay? All right. We are going on to 4.2, where we look at art galleries. Four point two begins with the question. Here is a floor plan for an art gallery. If you stand in the corner marked A, which walls or parts of walls can you see? What if you stood in the corner marked B? How many guards would you need, each standing at a corner, so that each wall could be seen by at least one of your guards? The guards can turn their heads, but they cannot leave their corners. Now, I used Word to make this and the guard A is actually in here, okay? And guard B is actually in here, okay? They're inside the building. They're not outside the building. So let's go ahead and draw this picture on a piece of paper, and we can go ahead and figure out the answer to these questions. Lined paper will be fine. Thank you for checking. So this is 4.2. We're looking at an art gallery. A straight edge is useful in this section, though. I had students who weren't using a straight edge and it wasn't coming out very well. So do use a straight edge. Even if it's just your ID, that makes a great straight edge. No, I forgot what the question was. What was the question? If you stood at the corner marked A, which walls or parts of walls could you see? Okay, so here's the guard in A. What can guard at point A see?
Just the bottom corner.
So this corner?
No, down on the bottom.
Down here?
Way, and then over to wherever that angle would, there.
Right there.
Yeah.
Okay, very nice. So you're saying the wall interrupts his view. So the wall kind of puts a limit on what the guard can see. So the guard can see through here and through here. Okay. Okay, so that's what the guard can see. But that wall blocks the view into these points, for example, even over to here. How about guard B? What can guard B see?
Everything except for the top two corners.
Good, yeah. So guard B can see all this rectangle, but it can't see up in here or up in here. So the line of sight radiates out from the guard. So he can see the middle because he can turn his head or her head, but the guard is unable to see up into those upper corners. This is why a straight edge is helpful. So you can see where the guard's able to see. Well, if we can see where the guard A and B can see, how many guards would you need to see the whole place?
1. You mean total?
Yeah, total.
Oh, sorry, yeah,
3. Okay, if we make the guards stand in the corners, then we need 3. Okay. So our guards all have to stand in the corners. How many of you have been to an art gallery? Anybody else? Yeah, me too. Yeah. Do you think that we need guards at art galleries?
No.
No, you don't think so? Are you being facetious? I guess that art crime is a big deal because the police don't have a lot of resources to track it down because they're so bogged down with other matters. Okay, well, we need at least 3 guards here to see everything. We're going to be looking at various art gallery floor plans today. So let's consider a few floor plans. So here's a floor plan with the opening is kind of a C shape. It has a little opening in it. Here's an art gallery that's just a rectangle, but it has a courtyard in the middle. Here's an art gallery that's a star shape. And here's an art gallery that's a rectangle, and then it has a few interior walls. So these are all different in a different number of ways. The kind of art galleries we're going to look at are like this star shape. This is called a polygonal closed curve. So it's made by straight edges connected end to end. So let's write that down. Polygonal closed curve. Polygonal closed curve. A figure made up of straight lines line pieces. Straight line pieces that are connected end to end. Connected end to end to form a loop. End to end to form a loop. So this kind of star shape is straight line pieces connected end to end to form a loop. Up here, this first art gallery we looked at is straight line pieces connected end to end to form a loop. Why is this C shape not a polygonal closed curve? What makes that not a polygonal closed curve?
It's not closed.
It's not closed. Good, it's got an opening. How about this? This is closed. Why isn't this a polygonal closed curve?
They're not all connected.
They're not all connected. Good. So always go back to your definition. That's very good. Not connected. This one is a polygonal closed curve. This one's not a polygonal closed curve because these ends aren't connected. Okay. Well, we're going to be looking at this polygonal closed curve. In fact, I'm going to ask you to make one. So you're going to make a polygonal closed curve. Then you're going to hand it off to the person next to you and they're going to decide how many guards that it needs. Now, make it using straight edges. If you have to use a straight edge, that's fine. I had some in the last class that had kind of curvy edges and some that were just sloppy so they couldn't tell what was going on. So do make a nice straight edge so that your person, if they need to, your person can take out a ruler and tell where the guards can see, okay? So you're going to make a polygonal closed curve, hand it to your neighbor, and they're going to see how many guards. The guards have to stand at the corner. Those are called vertices. In fact, before you hand off your polygonal closed curve, I want you to count the number of vertices. So count the number of vertices on your picture. It should be straight lines connected end to end. And then the person next to you is going to determine the smallest number of guards needed.
I don't even know if this is them.
What are vertices?
Corners.
Oh.
Yeah, so corners. So this one has 1, let me start, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 vertices on that star-shaped one. How many on the one on top? Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'm going to go around and collect this data. So after you get it done, I'll come around and I'll put it in a table. Let me get another piece of paper so I can. Yeah. Okay. So I'm going to go around and collect data on how many vertices and how many guards. If you're stuck, raise your hand.
Is this one?
Okay, straight lines, right? They're all straight lines, so they're connected? Yep. Okay, if you didn't find someone to switch with, I'll find you someone to switch with. You can find someone to switch. Do you two want to switch?
Yeah.
We gotta find how many guards.
Yeah.
Actually, I don't know.
Is this yours? That one? Yeah.
That is a power.
You gotta find how many guards.
I don't even know.
Man over here can see all that.
Yes. Yes. Controversy and trade with how many guards you need. Okay.
So what am I doing?
Vertices are corners.
Because I say, look,
I feel like you don't mean.
all this.
I don't know.
Did you trade already and figure out how many vertices? 4 vertices and how many guards? How about you?
9 and 4.
You cover it with
9
4.
9 vertices. I think we do less guards. Where did you have your guards?
Oh, she's tired.
You know?
I'm just going to
What, you want to,
Otherwise,
one here.
So you were like putting them all up in the car park, but it turns out that, I don't think they can see
How
it.
long am I supposed to
Yeah, no.
Okay, but
Well, there's a few
and
different.
there's a few different ways to arrange them, so we're looking for the least that.
The least,
I'm gonna put that right there. How many corners did you have? How many vertices?
No, 7.
7? And how many guards? 5. Okay, I think you can do it with less. So, for example, what if you have this guard right here? Where could that guard see?
That's when we got rid of got that 8.
A could see. So use your ruler to see where A could see. So A could see all the way down there. No, that one might be very effective in seeing up here and the whole gallery. Right, because we're putting a guard up here. Yeah, that one only needs one.
But that means, well, this one can't see all.
Nicholas, can you help people see how many vertices and guards they have, please? You don't even, because this one is at a point, so they can turn their head and look up into here also. They only need to watch it. How many vertices did you have?
Oh, vertices I had 7.
You had 7 also, but you only needed 1.
Yeah.
Were you able to get it down? Oh, so you got
Just
this.
2, really, right?
You have this one that's seen all the way up there. Yeah, yeah.
So really, just 2.
Okay, and how many vertices?
Yeah, but I just had 2.
8 vertices. How many are here? I think we get down. Where are you putting the garbage?
I just need 1
Okay. So, so this one can see all the way across there. One of the series in there, and one of the So three, could do, just do it less than. How about if you put one at one of these points right here, then they can see it this way, or this way. How about this one? And they can see up in here, and
The reason why I like showing up is like, I was like, one weird problem I was having with it, I just like, won't know how to answer it. It's like,
this guy can see
you know
out
what I'm saying?
there.
I just don't know how to do it.
You have 16 words. 16. Let's put it through them. Okay, how many verses did you have? 10 verses. How many guards? And how many verses do you have? Well, how many guards did you have? 9 verses. How many guards? How many verses did you have? And they can see up into that, and up into that.
Here it is, like,
So see if you can get down
technically it's 10 minutes.
So how many, did I ask you, how many did you have? So how many? Yeah, that's true. It's cold, but.
It was negative 14 outside, and that was south.
I don't mind the cold.
That's the worst part. I got off the text and
The thing is, if someone draws like a pentagon, you see the whole thing, like it's shaped like spikes out of the whole. That's what we need more. I feel like we just can't do this. It sounds like a great thing. Yeah, actually. Me and Trevor and Chase.
So you can get your number of guards down if instead of putting them up in the peak, you put them here. So, for example, a guard here can see up into this peak and up into this peak. So if you're at home working on this and you're wondering how do they get the guards down, that's how. So we have here a list of all the classes, number of guards, and number of vertices. You were all kinder to the people around you. Some of the last class had 27 or 26 vertices. You were kinder to each other. What we're going to do is compare this to the number of corners or vertices divided by 3.
Why?
Because we're going to see if you can see a pattern. So I'm going to take all the number of vertices and divide them by 3 and see if you can see a pattern.
But why 3?
You will see when I give you the pattern. So 4 divided by 3 is 1 1/3, so 1.3. 9 divided by 3 is 3. 7 divided by 3 is 2 and 1/3, so 2.3. I wrote that twice. 16 divided by 3 is 5.3. 10 divided by 3 is 3.3. 12 divided by 3 is 4. 9 divided by 3 is 3. This one we already did once. Okay. We did that one. Okay. 8 divided by 3 is 2 and 2/3, so 2.7. 5 divided by 3 is 1 and 2/3, so 1.7. 11 divided by 3 is 3 and 2/3, 3.7. 16 divided by 3 is 5 1/3. 6 divided by 3 is 2. 14 divided by 3 is 4 and 2/3. 12 divided by 3 is 4. 4 divided by 3 is 1 1/3. I think I did that one already. Yeah. 12 divided by 3 is 4. So I'm writing down the number of vertices divided by 3 and asking you if you can see any pattern between the number of guards that were required and the number of vertices divided by 3.
I'm thinking that last one isn't right.
Oh, it's not?
The last one.
Oh, yeah.
This one? So I'm taking the 12 and dividing by 3, and then I get 4. Okay. Can anybody see any relationship between the number of guards and the number of vertices divided by 3? Any pattern going on? Or relationship?
I was gonna say that they almost doubled, or doubled, more than doubled, but then some of them are
Some of them
not
did.
quite double.
Some of them are not quite double. Did we ever need more guards than this number?
No.
No. We never needed more guards than the number of vertices divided by 3, even though you all made very interesting and eclectic collection. That's what the art gallery theorem says. So we're going to write the art gallery theorem down. It's a little bit long. I don't know. Let's see, will it fit here? Yeah, it'll just fit. So we're looking at the art gallery theorem. Yes, there is really a theorem called the art gallery theorem. You can look it up on Wikipedia. The last class said, well, next you're going to tell me there's a serial bowl theorem. No, I don't know of a serial bowl theorem. Okay. All right, suppose we have a polygonal closed curve. Suppose we have a polygonal closed curve Suppose we have a polygonal closed curve in the plane. In the plane with V vertices. With V vertices. Then there are V divided by 3 vertices. There are V divided by 3 vertices from which it is possible to view every point on the interior of the curve. On the interior of the curve. If V divided by 3 is not an integer, then the largest number of vertices we need is the biggest integer less than V divided by 3. The biggest integer less than V divided by 3. We are able to see every point inside from less than or equal to V divided by 3 vertices. So the arc-Gallery theorem says, suppose we have a polygonal closed curve in the plane with v vertices. Then there are v divided by 3 vertices from which it is possible to view every point on the interior of the curve. If v divided by 3 is not an integer, then the largest number of vertices we need is the biggest integer less than v divided by 3. We are able to see every point inside from less than or equal to v divided by 3 vertices.
That's gonna be on
You'll have to quote that on the quiz. No, I'm just kidding. What?
So if v divided by 3 was like 2.3, then the largest number of vertices would be 2.
Perfect example. So if v divided by 3 was 2.3, then the most you would need was 2. Okay. We're going to look and see how this works out on Wednesday. Did you have a question?
Yeah, no, I'm good.
Okay. So we're going to look on Wednesday and see how this works out and look at how it plays out. I'll see you then.
I only fit so much on my note card.
Yeah. You don't have to write that on the note card.